Hi, this is Pat Kelly. Okay, in this problem, they want us to find the flux of this f function over some specified surface. Of course, they've given us that as well. And your formula for that flux calculation is this integral that I have here in purple. And a little bit more information that they give us is that we're only worried about the first octant in 3 space, and also that our n, our unit normal vector, is going in the upward direction. Let me tackle that one first. That last fact is with the normal vector going in the upward direction, that's relevant to me only because then I can do a quick rewrite of the formula. The formula for flux is here, but that equals, when that normal vector is in the upward direction, it equals this whole expression in orange. In a different problem, if you're told that the normal vector is in the downward direction, all you'll see is that this square brackets here changes a little bit. So use the other version of this in that case, all right? I love having that formula in front of me as I get going in a problem like this because it definitely guides me through what I need to do. And I can see really right off the bat what I need is these partials, whatever g of xy is. I need a couple partials in there. So first, let me remind you, your g function comes from this surface equation, and it's just all the stuff over here, which will be my g of xy. So g of xy is actually just z, okay? So you keep your eye on that as we get into our first step for this problem. Following that formula, this integral is going to look like, over some region, the f vector, I think I'd like to write that out, so I'm looking at it, the 3zi vector minus 4j vector plus yk vector. And I'd like to write that out so I can be looking at it as I, in my next step, do that dot product, because I need to dot that with. Now I'll follow through on this part of the formula by doing those partials. I know there's a negative sign, don't lose it. Partial of g with respect to x, so I'm looking at what I have here in yellow. Differentiated with respect to x, you can see that that's just going to be a minus 1, but there is this minus, so that just becomes a plus 1 times your I vector, so that behaved nicely. Minus, now I go to do my partial with respect to y of the same thing, the yellow, that's also negative 1. With that minus, that'll become plus. And that behaved nicely as well. And the k, there's no differentiation or anything involved there. That's just k vector as part of the formula. Okay, and then dA. Okay, so now let's go ahead and do that dot product. If I slip down a line here, this equals the integral over the region. We've done a couple hundred dozen dot products at this point, right? 3z plus multiplying these, I'm just getting a minus 4, and then plus y, looks good, dA. And what I'll do in my next step, I can just do this over, is let's get everything in terms of xy, okay? So the region, I still want to think about for a little bit, so I'll space out my integrals. We're going to put some limits of integration in there with respect to x and y. I want to get everything in terms of xy, so even right off the bat, there's a 3z. You want to see that as 3 times what you know z equals in terms of xy. That's your 1 minus x minus y. And then minus 4 plus y. And even that dA, I want to get in terms of x and y. So it's going to be dy and dx, or maybe dx and dy. It depends the order, and it's actually up to you. Usually what depends is if one of them is a little bit more complicated than the other, but neither is in this case. So I'll just do dy dx. And then I'm going to get my limits of integration. So first I want to look at my y limits. This is where I'm going to go up to that surface equation. And what you're actually looking at for this area, what's capital A for us all the time, is like the cross section of this surface down on the xy plane. It's like a projection. And I'm just talking through that because what you do mathematically is you put a 0 in for z. that means you're down on the xy plane, okay? So we're looking at just this 1 minus x minus y, and if it were to equal 0 on the other side, then if you can imagine, throw the y on the other side, and you've got yourself y as a function of x, y equals 1 minus x, and that becomes my upper limit of integration here, 1 minus x for that inner integration, upper limit. And the lower limit, this is where I needed to know that it did specify we're in the first octant. Okay, so we're only going to start at 0 and go up to that 1 minus x. Also for the x variable, knowing that I'm in that first octant is going to take me from 0 to 1. Okay. All right, so this is my integral now. If you're looking at it with just x's and y's, it's a lot more friendly than we might have thought. So let's just go ahead and do this. Slide over here, and I think, let's see, do I need a cleanup on that? Not too much. I'll do a little bit of cleanup. I like to collect my like terms, so I'm looking at just minus 3, integral 0 to 1, integral 0 to 1 minus x, looks neater anyway, minus 3x. My y's are going to look like minus 3y plus y minus 2y. And I do have a constant 3, take away 4, looks like minus 1. Now that looks very friendly, I think. We can do our integration, dy dx. So my outer integration is still going to be 0 to 1 for the x variable. Inside, with respect to y, this is looking like minus 3xy. Minus 2y becomes minus y squared, minus y. And I have to do all of that from here, 0 to that 1 minus x. And then dx. We ready for that? I think so. Dx there, okay. Now let's plug the limits of integration in. I'm going to have to come down here for some more space. 1 minus x plugged in there for y. I'll still have my limits and my integration for x. And then minus 3x, 1 minus x, minus 1 minus x squared, and then minus 1 minus x. Okay, now that's just my upper limit of integration. Let's make sure you're keeping track of where you're at. Then we'd plug in the lower limit of integration and subtract, but it's so nice when that's a 0 and there is a y everywhere, so that's all going to be 0. So I think we're actually done plugging in, and then this is all still dx. Okay. I would like this to look nicer, cleaner. You're hopefully seeing this is just algebra, right? But worth doing, I think, to make the integration go a little bit more smoothly. Let's go ahead and collect some like terms. If I could do a little bit of algebra, even in my head. Minus 3x minus x, there's plus 3x squared, positive 3x squareds. This is going to be plus x squared, but minus. I think I'm down to 2x squared, and I think that's it for the x squareds. Okay, my x's look like minus 3x. From here, I'm going to have minus 2x. That'll be positive, though. So plus 2x, take away 3, I'm down to a negative x. Plus x. Looks like that blanked out to 0. My constants, I'm done there. This will be a minus 1, minus another 1. Looks like minus 2. That looks very friendly. dx. Okay, now let's do that integral. This is getting into Calc 1 stuff, I think, now, right? 2x cubed over 3 minus 2x, and I have my limits of integration 0 to 1. Let's plug them in. I like both those numbers. This is going to be 2/3 minus 2. Subtract, when I put in the 0, of course, that blanks out. So I think I'm looking just at 2/3 take away 2, which is what, 6/3, 2 take away 6 minus 4/3 minus, be careful of that, 2/3 minus, and this is going to be 6/3, 2 minus 6 is minus 4/3. Pretty good about that. And that would be my final answer. Okay? Go try some on your own.